Good afternoon, everybody. Please. So first of all, an announcement. I had a request to move the exam that I had said is going to be next Tuesday, 1 week from today, to move it to Friday the 13th. Okay. So if I don't have any objections by tonight, by email, I'll move it to Friday. Okay. So now, if you have a conflict of any kind, please let me know, and then we'll keep it on Tuesday. Okay. Any comments on that possibility? How many yays? How many nays? Yay. Okay. All right. So again, if I get an objection by tonight, then I will not move it. But in principle, I'm moving it for Friday. Okay. In that case, what we'll do on Friday, we'll talk about image segmentation, and we will do the review on Tuesday. Okay. So I want to make a review, the lecture before the exam. I'm going to give you a makeup test. So when I'll send email to everybody so you are aware when the exam is going to be. And I'm going to post the practice exam very soon. Okay? All right? All right. The other thing is that on Tuesdays, I rather have my office hours in the lab rather than my office. So if you need to talk to me about the homework or anything, please come to Hayden in the basement. Okay, we're going to be there working with my students. All right. Any questions, comments? No? Okay. All right. So the plan for today then is let's talk about the half transform that I started talking about last class. And after that, we'll talk about ransack, which is a method for removing outliers from data. And if we have time, we'll talk about active contours or snakes. Okay? All right. So what we're doing is slowly progressing into higher level features, right? We started with cleaning noise, so at the pixel level. Then we started doing edge detection, again at the pixel level. Then we went to corners, which involves a little more than just 1 point. It's a neighborhood. And now we're going to go into higher level like lines, circles, or general contours, okay? So we started talking about this last time, okay? We said, well, let's say I want to find a line, okay? And so we started by writing the equation of a line. And we wrote the slope-intercept equation of the line, where here m is slope, n is intercept, and those are the things that we think of parameters of this equation. And x and y are the variables. So as we move points on the line, what happens, x and y change, but they all satisfy this equation for that given m and n, right? So if I have point x1, y1 on the line, it has to satisfy the equation. If I have another point, it also has to satisfy the equation and so forth, right? Okay. Now what we did was to look at this equation in a slightly different way. We said, okay, let's reverse the role of these variables and think of m and n not as the parameters, but as the variables, and x and y as some fixed parameters. Okay? So we went from what we call the image space, where we are looking for lines, to the parameter space. Okay? So in this case, I have two parameters, m and n. So I have a two-dimensional parameter space. Okay, in one axis I have intercept, in the other axis I have a slope. All right? And then a line here that has associated a pair of m and n can be represented in this space as a point. So from lines in the image space, I went to points in the parameter space. So if I have more lines in the image space, each of these lines will represent a point over here. And what we have now is this back and forth. I can go from points to lines and from lines to points. Yes? Okay. All right. So this is, again, the same thing. Okay. So now if I have, oops, sorry. Here. All right, so now what I do is, if I fix a point on the line, okay, and now I look at all the lines passing through that point, what happens in the parameter space is that now I have a line that passes along all the points that are compatible in terms of the slope and intercept with a given point, right? So in this equation now, right, n and m are now the parameter, are the variables, and x1, y1, which was a fixed point in my image space, become the parameters. So now I have, and this is also the equation of a line. So now I have a line, and every point in this line corresponds to a pair of slope and intercept that will correspond to a line passing through the point x1, y1 in the image space. Yes? Okay? Questions? All right. So in image space, we consider lines, points, or collinear points. And that in parameter space, what happens? Well, I would say that a line will correspond to a point, and a point will correspond to a line, and collinear points will correspond to intersecting lines. Okay? So here's the half transform technique, and it's really a technique that's more general than finding lines. So in this class today, actually we're going to talk about how to find lines with a half transform, how to find circles, and how to find any genetic closed contour. Okay? So it's more of a way of thinking of the problem than really finding just lines. All right? So, and the idea is that we take a problem that in principle is difficult in the image space, and we make it easier by going to the parameter space. Okay? So my goal here for now is that I have a problem which can be described in terms of parameters in the image space, and then we're going to move the parameter space to actually do a voting scheme to find those parameters. Okay? So, given an edge point in the image, right, I have an infinite number of lines passing through that edge. And what I want to do is represent that point in the parameter space, okay, slope and intercept. So this guy is going to vote for all these possible slope intercepts, okay? And of course, the line, the green line over here, corresponds to one pair, Mn. In this case, the intercept is positive, the slope is negative, so maybe a point like there. Okay. All right. So if I have a set of edge points that are all collinear, right, each point will go to a line in parameter space, but all those lines should be intersecting in one point, which is the point corresponding to the slope and the intercept of that line. Okay, so I have multiple lines here. Each line over each edges, each point gives me a line over here, and if I have multiple points that are aligned, they will be agreeing on one particular slope and intercept. Okay? All right. So last time, I introduced the idea that I'm going to look at this parameter space as an image. Why can I do that? Well, it's a two-dimensional space, right? So I can think of a slope as the rows and intercept as the columns, for example, right? And I can display that in an image space, and I can look at it as an image, okay? Now, the idea is that I'm looking for places where all these lines intersect. So I will have a very bright point at the place where all the lines in the parameter space happen to converge. So if this is the image space, and this is the parameter space, right? And I have these guys that have been found using an edge detector. Each of these guys will give me a line here, right? And all of these guys agree in a particular slope and intercept. In this case, this line has a negative slope. Let's say slope here, intercept here. So it has a negative slope and a positive intercept. So something positive intercept, negative slope. So something here, right? All these lines that come from all of these points should be intersecting over here, right? So I could paint this in an image, right? And when I look at this image, I'm going to see these stars, okay? These stars indicate that I have a lot of points that agree in one pair of slope and intercept. If I have another line, I will have another star, right? So by counting these stars, I know how many lines I have. Okay? Now, we discussed that last time before we left, that this equation was not the best choice for this problem. Anybody remember why?
What's a straight line? Sorry, x equals a constant.
Right, so if I have a line of the form x equal k, right, I cannot write in this form, right, because this is assuming that the coefficient in front of the y is not 0. Okay, so that's one problem. What's the other problem? How big do I need to make this image? I need to make it very, 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 very big because the slope can go to infinity. Okay, so I don't have a finite domain. Okay, so we said that instead of doing that, we were going to work with an equation that looks like this. Okay, so if this is the image space, now I have rho in one axis, theta in the other axis. Sorry, that's for parameter space. In image space, I still have x and y. And if I have a line like this, rho measures this distance from the origin to the line along the normal, and theta is the orientation of the normal. Okay? Now in parameter space, still 2D, but now I have rho and theta. Okay? So I went from slope intercept to distance from the origin to the line and orientation of the normal, which gives the orientation of the line, right? Okay? So still 2D. Now, why do I prefer this? Why is this better than this? Does it solve my two problems? Can I represent lines like this? Yes. Right? The coefficients of x and y could be anything now. All right? Do I solve the problem of the very large infinite image in a parameter space? Yes. Why? Right. So theta, for example, there are different choices of or conventions. I can do, for example, theta between minus 90 degrees and plus 90 degrees measured from the horizontal axis. Okay, that's one possibility. I can do it also from 0 to pi. Okay. How about rho? Rho is the distance from the origin to the line, right? So depending where I put my origin, if I put it in the center of the image or in the corner, but you know, how far can it be at most it will be the diagonal of my image. So it's also limited. Okay? So I have now a finite image. Okay. Now, here I said I went from lines to points, and from collinear points to these stars things. Okay? What happens when I change this equation? Do I still have something that looks like this? Let me do it here. Suppose I have in image space this square. Okay, so this has coordinates 1, 1, this has coordinates 1, 0, this has coordinates 0, 1. Okay. What is the half transform of this point A? How does it map here?
Theta is 90 and rho is 1.
I'm talking about a point, not of a line. So I erase it here, right? So I have that for a point over here, the half transform was a line, right? And for a line, the half transform is a point. Okay? So now I'm asking, let's fix this point, the point A. What is the half transform? If it was here, let me draw the same square over here. Right, this guy is 0, 1, right? So this point over here will give me a line over there, right? Which will be of the form so I'm plugging here x is 0, y is 1, right? So I have 1 is equal to n, right? So the line corresponding to this point will be a line that has intercept 1. Okay? So let's do the same thing here. I have a point that has coordinates 0 and 1. And I'm mapping this point in parameter space. What I mean is I want all the points over here, all the pairs, rho and theta, that gives me lines passing through this point 0 and 1. Okay? So what do I need to do? I plug x, y the same way I did here. I plug x, y here, right? So that means for A, right, I have that rho has to be equal to x, which is 0, plus y, which is 1, times sine theta. Yes? So that means that the half transform of this point now is no longer a line, right? What it is sine of theta, right? So let's try to keep this as clean as possible. So I'm going to go from minus 90 to plus 90. Let's say 1 is here. Okay? So sine of 90 is 1. Sine of minus 90 is minus 1. So this curve over here is the half transform of A. Yes? Okay. All right. Now let's do the half transform of C. What's the half transform of C? C will be rho is equal to cosine theta, right? So let's draw cosine. This is C, okay? How about this point over here? Where's that point? What does that point represent? A line, okay? The line joining A and C, right? So it's this diagonal here. Let's see if that's right, okay? So this point over here is when cosine and sine are the same, right? So this is at 45 degrees, right? And how much is this? Square 2 over 2, right? Okay, now let's look at this diagonal over here. What's the representation of this line in this half space? Now I need rho and theta, right? So how do I find the rho and theta for this line? Perpendicular, measure this much. How much is that? This is half of the diagonal of the square. So this is square root 2 over 2. And the angle, of course, here is 45 degrees. Okay? So lines are still intersection of these curves. But now the curves are not lines anymore, they're sinusoidal curves. Okay? How about the half transform of the point B? It would be rho is equal to cos theta plus sine theta, right? So can I draw that? Well, let's try. So in 0 is the sum of these two curves, right? I'm going to do so 0 plus 1, that will give 1. So at 0 will pass through here, right? Over here, they're both the same, so it will double. So this will be square root of 2, right? Over here is 1 plus 0, so it's going to go here. At minus 45 degrees, these two guys cancel out. So the curve will pass here. And then over here, 0 plus minus 1, it will pass here. So my curve would look something like that. Okay? So what is this point over here? That's the intersection of A and B, right? So this should be the line AB, okay? The line AB is this guy over here. How much is the rho for AB? 1. And how much is the angle? 90, right? 91. Checks. Okay? So the thing is, I can go back and forth from here to here and from here to there, right? And again, the way I find lines is by finding multiple intersections of these curves, right? Of course, there's always a line between 2 points, right? So finding just one intersection over here doesn't say anything. I can always find a line there. But if I have many points that happen to be on the same line, then I will have a lot of curves that will pass through that point. Okay? Let me see if that demo I have here works. Not this one. Okay, doesn't want to cooperate. It was working at my office. Let's try this one here. Thank you. Okay, so here what you see is a bunch of points that I clicked, right? And for each of these black dots, I get a sinusoidal curve in the parameter space. And because they're all roughly on the same line, they all sort of roughly pass through the same point over here. Okay. Now, if I click over here, it will draw that red line, which is roughly a line. Let me see if I can add more points to see if it works. Yeah, so. And if I click here, that's the line. Okay, so I can construct that image over there, and now I can process that as an image. Okay, now let's see how do I construct that image in, like if I wanted to implement this in MATLAB, how would you do it? How do I build that image? This is the algorithm, okay? Some guy gives me the output of an edge detector, okay? And by this, right now, I'm going just to consider the magnitude of the output of the edge detector, right? So at every pixel in the image, we compute the gradient, and then we find the magnitude of the gradient. And we know if that gradient was greater than a certain threshold, we say that's an edge, and lines are made of edges. So I'm going to consider all those edges that were greater than a threshold as my input. Okay? Now what we're going to do is we're going to build an image. So right now my image is empty. It's all black. Okay? That image is the parameter space image. Okay? And I'm going to have rho as my vertical axis and theta as my horizontal axis. All right? And I'm going to paint that image. Okay? How do I paint it? For every edge in my input image, I'm going to try to draw a curve. Okay? Now my image is discrete. So what I'll do is I will scan each column to paint my image. So I have an edge in my image. This edge has coordinates x and y. Okay? Now I'm going to paint this other image where now I'm doing in this direction rho, in this direction theta. So what I'm going to do is this first column represents minus 90 degrees, and this last column represents plus 90 degrees. Okay? How many columns I'm going to have? Well, it's up to me. What I'm going to do is I'm going to discretize this 180 degrees. Okay? So I'm going to have a delta theta that I'm going to set. Let's say every 5 degrees. Okay? Okay? And how many rows do I have? Again, it's up to me. I'm going to discretize, okay? But I'm going to divide d or minus d over 2 to plus d over 2, okay? Now, for this x and y, what I'm going to do is plug it in my equation, right? My equation said that rho was equal to x cos theta plus y sine theta. Right? So this x and this y is this and that. Okay? Now I need to draw this sinusoidal here. How am I going to do it? What I'm going to do is I'm going to start with theta from minus 90 degree, plug in minus 90 degree here, right? So I have x times cosine of minus 90 plus y times sine of minus 90. That will give me a rho. That rho is going to be a double number, right? Now what I'm going to do is figure out in which bin falls in, okay? And in that bin, for the minus 90 column, I'm going to add 1. Say my curve passes through here. Then I change theta to minus 85, okay? And plug it again. I get a new rho. Again, I figure out which height goes, and I add 1 over there. Okay? So I will be drawing this curve by putting ones wherever that curve crosses by, right? And I do that again from minus 90 to plus 90. Okay? Make sense? Yes?
I have a question on that. So the line A and B intersect at that rightmost point. But what about the leftmost point?
Very good question. Yes. So what's this point? This point has what? Minus 90 and rho minus 1. Right? Okay, so let's write the equation for that. So it says minus 1, right, is equal to x cosine of minus 90 plus y sine of minus 90. Okay? What is cosine of minus 90? 0. What is sine of minus 90? Minus 1. Right? So what I get is minus 1 is equal to minus y, or y equal 1. So it's the same line. Okay? And one thing I forgot to mention is on the slides, with the convention I just picked, that theta is between 90 and minus 90. In this quadrant, lines are like this. Rho is positive and theta is positive. In lines like here, rho is positive, but theta is negative. And lines here, rho is negative and theta is positive. And lines like here, rho is negative and theta is also negative. Okay? You guys should check it. Write the equation for a line on each of these quadrants and see how that's true. Okay? Yes?
So then why are we interested in that section of minus 90 to 0 if it's just a repetition?
Well, they are not. That's because this is just a particular case. What happens is it's an ambiguous case because I'm talking about the length AB, which was this guy, right? And so this normal over here, I can think of having plus 90 like this, or minus 90, okay? But it is just because it's the vertical. Okay? But if I have something that is like this, I need that, okay? Good question. All right, so going back here, I'm painting my image, right? So far, this image is going to be very dark, right? Because I have all zeros, which is black. And then I have put a 1 in each of these pixels corresponding to the curve for this guy, right? But then I move to the next edge. And let's say the next edge I'm moving is here. Okay? I will not be doing it like that, right? I would do raster scanning from here to the bottom. But let's say it was this. This will give me another curve, right? So I'm going to add 1 to whatever that curve passes, right? Now, again, 2 points always define a line, so 2 is still too small. But these two guys have to agree on the slope of that line, which means that the curve for this guy and the curve for this guy must intersect at the point corresponding to the rho and the theta for this line. Okay? So what I'm going to happen is when I paint the other curve, at some point I'm going to intersect here. And that guy now has 2 instead of 1. Right? So now it's a little brighter because I have 2 points that say, I think there is a line with this particular rho and this particular theta. And I keep doing for all the image. And what happens is, if I did have a lot of edges on the same line, this guy that now is only 2, when I did all of that, this will become how much? What will be the number there? The number of edges that are on this line. Okay? So again, you can think of this as voting. Every edge is voting for a set of rhos and thetas, and this being will be the winner with all the votes agreeing on this particular rho and theta. Okay? So when I look at this image, it will be very dark with faint white curves and very bright spots where the lines happen. Okay? So how do I find lines in this image? I scan it, I create this image, and now I need to look for bright spots. How do I find bright spots? Thresholding. Very easy. So after I threshold, I will know the rho and theta for this line. So I would say there is a line in my image that has this rho and this theta. How do I know which edges belong to that line? So I could do 2 things. So one thing is, now that I know that there's a line rho theta, I can go to the image space and sort of draw the line, figure out where that line will pass through, and see how many edges are on that line, and then assign them. That's one way. So I would do a post-processing. Okay? Another possibility is that when I'm voting for pairs of rho and theta, I record who votes for what. So to each of these accumulators, to each of these bins, I attach a list of the guys that said, I believe there is a line with this rho and this theta. Okay? So associated with this will be, for example, a linked list that has the x and y's of all the guys that said there is a line with this rho and this theta. So when I'm done and I figure out that this guy has a high count, I just pull this list and tell me which edges are on the line. Okay? Right? So what happens if my image was something like this? These edges will believe that there is a line that has passes through here, rho and theta, and this edge just believes that too. Okay? So what this is going to do is give me all the edges that are on the same line, regardless whether there are big gaps or not. Okay? So to process these gaps, I will have to do some post-processing. I will have to scan the list and see if there is a gap because there was a misdetection of an edge, or because indeed it's a very large gap and this was just one segment and this was another segment that happened to be aligned with each other, right? So we have something that it was like a new shape, right? So I don't have a line there, right? So this will tell me that these guys and these guys are on the same line, but it will not tell me that they need to be two separate segments. Okay? Questions? No? Okay. So we have an algorithm, right? So I told you how to find lines. And one of the nice things that I should point out of the half transform is that I don't have to know a priori how many lines I have in my image. Why is that? I'm not looking for 2 lines, 3 lines. How many lines will be detected? As many bright spots I found. Okay, so if I have 2 bright spots, then I have 2 lines. If I have 5 bright spots, then I have 5 lines. Now, I'm just changing one problem for another because now I'm saying how many edges I need on a line to tell that there is a line, right? I had to pick the threshold that would say this guy is bright enough. Okay? But if I decide on that, how long the line has to be, then I can find any number of lines in one shot. Right? I just build this image, I threshold, all the points that survive my threshold that tell me which lines. And if I kept track of the identity who voted for each of these bright spots, then I also know the pixels that belong to the line. Okay? Cool? All right. Can I make this algorithm more efficient? Yes?
Once an intersection is found, just calculate values close by to that for the remaining points.
No, I mean, I found the intersection, I have the things, and then I have the line. You had another?
Once you have an intersection, see if any other point will satisfy that intersection.
I could do that, yes. That would be one way. But to the beginning, can I make my image in the parameter space a little simpler, a little cleaner, less clutter in it? No. Think about the input. What did I use as my input to generate that image? Where did I start? with the whole image. I got my image, and then I did something to that image. What did I do? Edge detection, right? And the edge detector works by doing what? The gradient, and then I say, let's pick the pixels that have large magnitude of the gradient, right? I threw away half of my information, right? What did I throw away? What's the other part of the edge detector? It's not only the magnitude, right?
The direction.
It's the orientation, right? Can I use that orientation?
You could focus on points that match the orientation you know.
Right. Why? How is that? Let's look at what happens to my image. Suppose I have something like that, right? And then looking for the lines that make the boundary of this white box, right? So I'm going to do edge detection. I'm going to find the gradient at everywhere. So over here, this image is fairly black flat, so the magnitude of the gradient is 0, right? But on the boundaries of this thing, the magnitude is large, right? So how is the gradient vector in a point in this boundary? How does that gradient vector look like? Perpendicular, right, to the edge. And it's large because there is a big change from dark to bright. Okay? So what's the orientation of that gradient? Is this theta the same theta I had there? Yes. Okay? So given this edge over here, I know that it's a candidate to have a line through it with orientation theta of the normal. Okay? So what that means is that when I plug in here, I plug x and y, but I can also plug theta. Okay? So instead of varying theta from minus 90 to 90, scan the whole row, right? I'm just going to have one value of rho that's compatible with that, right? So that says that for the given theta, I figure out which column that is. I compute the row, and I add plus 1 right there. Okay? So instead of scanning from minus 90 to plus 90. That saves computation and cleans the image. I don't have as many competing curves that might confuse things. Okay? There's only one problem with that. What might be a problem?
Can we do the increment by the magnitude of the brightness?
Yes, we could do something. We can do a weighted voted. So the bigger the magnitude, the more strong I believe that I have an edge here. That's a very good point. Okay. Now, what else? I don't know. The sound is. What else can I do? What else should I be aware of when I do this? You were concerned about that last time. Noise. Okay. So this is assumed that my theta is perfect, right? But if theta was kind of, the line over here, the edge detector was a little crooked, right? I would be voting my single vote. Now this guy is only voting once, right? And he might be voting in the wrong place. Okay? So typically, if you're going to do that saving, you still not vote only one guy, but you vote in a small neighborhood around it, just to make sure that I don't miss anything. Okay? It's just that I reduce my computation time that way. All right? Questions?
To calculate the average of all the permutations, you use that.
Sorry, say that again.
To get the average of all the orientations of within that area.
Well, what will happen is when I threshold, right, I might get not just one pixel that's very bright. I might get a spot, a blotch that, 50% of my pixels voted for this beam, but 25 voted for the next door beam, and another 10 on this beam. So where do I do it? So I have to do some kind of weighted average and decide what is the orientation. Okay? And then the end, something that we're going to do in 5 or 10 more minutes, is after I have my list of edges that belongs to that, what I'm going to do is fit the line to that, right? So if you give me now these edges, I think they belong to the same line. Now what I'm going to do is find what is the best line that's a good approximation of all these data points. Okay? So some of them might be on the line, but some of them might be slightly off. Because after all, this was discretely sized, right? So this only allowed me for theta to be minus 90, minus 85, minus 80. What if my line was 72.3? Okay? It will not really give me that accuracy here. I still need to do this fitting. Okay? All right? Okay. Now we are ready to the next step. Suppose I want now to find circles, not lines. Okay, so my image has a nice circle over there. Okay, let's say is the moon, right? So I have a white, big, round thing there. Okay, and I want to detect it. Okay, or I might have an image that has a bunch of coins on it, and I want to figure out how many coins are there in the image. Okay, so how do I do what I just did for the line, but to detect circles? How do I modify the Haft transform to solve this problem? So we're all engineers, right? So whenever we have a tool, if we have a hammer, everything becomes a nail, right? So how do I have a nice tool that found lines? Can I morph it with little changes to find circles? How did we start the whole thing? What was the first thing I did? I wrote the equation of the line, right? So let's write the equation of the circle, okay? What is the equation of a circle? Let's say my circle has center AB and radius R, right? How do we write the equation for that circle? Right? All right. Okay, so how do I use this for doing Haft transform? What does that mean?
Variables and keep x and y constant?
Right. We flip the role of the variables and parameters. Now, just A and B?
A, B, and R.
A, B, and R. Okay, so now I have 3 parameters, right? And that means that my parameter space is no longer an image. It's a volume. Okay, so I have access now for A, B, and R. right? And really, I'm going to discretize it because, again, I'm voting, right? So what I'm going to do is make a grid of possible A's and B's and possible radiuses. Right, so it looks like a Rubik cube. Okay? So how do I apply half transform? What do I need to do? Start in the image. So the first step is always edge detection. Right? So I find edge detection. So this now becomes like that, right? And for every edge, might be a circle, might be not, I don't know, right? If I knew, I don't have to do this. So for every edge that I find, I'm going to vote for circles that are compatible with that edge. Okay? So when we did the half transform of lines, a point corresponded to a sinusoidal curve. Okay? So here, if I'm looking for circles, if I take an edge over here, what's the half transform of that? How do we do it for lines? Come on, guys. Work with me. How did we get the sinusoid for the line? What did we do? We plug in x and y in the equation, right? And then reverse the role of the parameters, and we look at what the equation was at. Okay? So let's do the same thing here, right? So I fix a guy. Let's call this guy as x1, y1, right? Plug it in here. So now x and y are not variables anymore. It's fixed. What's variables is a, b, and r. Okay? This equation, using a and b and r as variables, what does it represent? A cone. Good. Why?
So every R, A and B is
Right. So if I fix, I'm sorry, my tongue. If I fix the radius for each radius, possible radius, this is equation of a circle too, right? But where is the center now? X1, Y1, right? And the points around it, the points on the circle, has coordinates A and B. Okay? So if you think about it, it makes perfect sense, right? So I'm saying this guy might belong to a circle. Okay? If it belongs to a circle, where is the center of that circle? It has to be a distance r of it. Okay? So it has to be in a circle of radius r. Of course, I don't know which r, right? So I really have a set of possible circles that are all compatible with this guy. And the centers have to be in one of these circles. Okay? So I draw them here flat, but if I draw this in this volume, what it means is I have a cone, right? I have bigger and bigger circles as I move deeper in this cube. Okay? So how would I find circles? I do this voting for every pixel, right? And where would be a hit? A hit will be when everybody agrees in a set of parameters, the same A, B, and R. So when I have a lot of intersections of these circles, I have a triplet that now has the center and the radius of the circle. Okay? So I could apply it to circles exactly as I did with the half transform for lines. The price I'm paying is what? the size of this space that I will need to threshold and search for bright spots is larger, right? Because now it's 3D. Okay? I can apply the same procedure to any curve, but I can write an equation. The trick is reverse the role of variables and parameters. Okay? And then you vote for the set of parameters that are consistent with my data. Okay? All right? Can I make this more efficient? What did we do to make it more efficient in the lines?
Add a direction.
Add a direction. Can I use the orientation here? What does the orientation tell me in a circle?
Towards the center.
Towards, it's perpendicular to the tangent to the circle. Okay? So if this is a tangent, right, the gradient is perpendicular to that tangent. So if I know the orientation of the edge, I know basically the orientation of the tangent. Why is that helpful? You sort of said it.
Yeah, I mean, when you find the intersection point of all those tangents, it would be the center of the circle.
Well, before, right, the circles that the centers that were compatible with this guy were in a circle. But if I give you the tangent of that circle on that point, where are the compatible centers? On the line perpendicular to the tangent, right? So now instead of having circles, what I have is that line over there, okay? Can we derive this using equations? And the answer is yes. How we do that? Like we did for the line, what we're going to do is change the way we write the equation of the circle. Can you think of an alternative way of writing the equation of the circle in a way that uses this orientation theta that the gradient is so nice to give it to me? Hint, I need two equations. Nobody? X equal to? Yes? Okay? Everybody agrees that this represents the same circle, right? Okay, so now what I'm going to do is I'm going to eliminate the radius from these two equations. Okay? Because I have already 3 parameters. I don't want 4. Okay? So what I'm going to do is throw away the radius, okay, and just think about A, B, and theta. Okay? So how do I do that? Let's do the division of one over the other. Right? So I have that y over x. Sorry. Let me simplify it. Let's do x minus a is equal to r cosine theta, and y minus b is equal to r sine theta. And then do the ratio of these two equations, right? So then I have that y minus b over x minus a is equal to tan theta. Right? So I can write this now as y minus b is equal to x minus a tan theta, or I'm just going to write it prettier, but we're already done. Okay, I'm going to write it as b is equal to a tan theta minus x tan theta plus y. Okay? And why I want it this way? Because now it's very clear to see that this is an equation of what? Of a line, right? In terms of A and B. Slope-intercept type of equation, right? And now given an edge in my image, where I know not only that's high magnitude of the gradient, but I also know its orientation, I can plug in theta over here, x and y, right? And that gives me the line that's compatible with that point being on a circle. Okay? And so now finding circles becomes, again, finding places where all these lines intersect. Okay? Now, what happened to the radius? How do I get the radius? So again, I lost it here, right? So one thing I can do is go back and see who voted for this circle, right? And based on those points, I will find the radius that's compatible with that, okay? Now, similarly, that the problem that I have with two line segments that happen to be aligned, if my data happen to have concentric circles, they all agree on the same center, right? But they have different radius. So I will have to be able to distinguish that. Okay? If I know the radius beforehand, then I don't have any problem. But make sense? Okay? Ready for the next step? I want to detect these things in my image. Wow, it doesn't look exactly the same, but pretend it is. Okay? And I might have other stuff here. So, how do I find that clove leaf using the half transform?
First time equation of it?
Okay, yeah. That's the trick I told you, right? So I need a parametric equation. I don't know the parametric equation of this. I just made it up. The only thing I have is an example. What do I do? Again, think, have a hammer, everything is a nail. How do I make the problem similar to what I just did? This is sort of a circle, right? It's a funny circle. I just squish in some places and pull in others, but still a closed contour. Okay? So since circle, I erase it, we're represented by a center and a radius. Okay? This guy really doesn't have a center and it doesn't have radius, but I'm going to do this, right? I could think of this being mapped to this. Every point over here could go to one point over there. So what I'm going to do is arbitrarily, in that example that you gave me, say I'm going to pick this point as my center. And if I could be outside, but I'm just going to do it inside. Just a point, a reference point. Okay? And then what happens is every guy here have their own opinion of what the radius has to be, right? They don't have all the same radius. Okay? So the radius depends on the point. Okay? So instead of being a constant, is going to be a variable. Okay? All right, so what we're going to do is this. We're going to learn this shape. I don't have the equation, but I can learn the shape. How am I going to learn the shape? Well, you give me this example, so I have like an image of this guy first, right? So I do edge detection on it. All right? And so now what I'm going to do is for every point that my edge detector found, I'm going to record the radius for that. Okay? And not only the radius, but also the orientation of the line that goes from the point to the center. Because in the circle, that center was perpendicular to the tangent. But here it's not. If it was, then everything would be a piece of a circle, right? Which might not be. Okay? So I need the length of this and also the orientation of it, which again doesn't have to be perpendicular to the tangent. Okay? So for each point over here, I do have a tangent though, that the gradient gave me that. Okay? And that tangent has some angle with respect to my reference. Let's call that angle phi. And again, this angle varies as I move on the curve. Okay, so let's call, if this is a point I, let's call this angle phi sub I. And then I have this radius that goes from this point to this center. Let's call the center AB. Okay? And so this distance, the length of that radius, let's call that R sub I. And the angle that this radius makes with this reference line, let's call it alpha sub I. Okay? So now what I'm going to do is I'm going to record what I just learned. I do this for every point on the curve, right? So I'm going to record that my curve is made of guys that have the orientation of the gradient is phi sub I. And if I am there, I will find the center by moving along this radius with an orientation alpha sub I at distance R sub I. If I did that, I will get here. And I do that for every point. Okay, so this guy J is phi sub J, it has is alpha sub J and Rj. Okay, so I'm going to record this. Now, I'm going to record this in a particular way. What I'm going to do is I'm going to record it in a hash table. Okay? Who remembers what a hash table is? Yes?
You apply a function to a value and you just get a semi-unique like identifier, and then you kind of store that identifier. The smaller your table, the less unique identifiers you get, so you have to stack them up.
And the advantage of doing that is, do I want to do this?
If you have an infinitely long hash table, it's just one operation. You just calculate it and you just get your value. But it's just more.
I have instant access, right? So it's like knowing exactly where to look for my information. Okay? So I have a very large space, so it's not crowded, so I don't have collisions. And what I'm going to do is map my data into this hash table, so I can retrieve it easily later on when I need to do my detection. Okay? Now, what I'm going to use as key for the hash table is this angle phi sub I. Okay? Why is that? Because this is something that it will give me, I'll get that from my gradient operator right away. Okay? So I don't know if an edge over here belongs to this shape or not. But definitely I know the orientation of this gradient. Okay? So given the orientation of this gradient, I have some phi. With that phi, I'm going to come over here on the table. Okay? So this is the key, how I enter to the table. Okay? Now, what will be recorded in this row associated with this key? What I'll associate with it is R sub I and alpha sub I. Okay, so you tell me the gradient, and I tell you how to find the center from that location. Okay? So I have here a pair that says alpha sub I, r sub I. Okay? Now, do I have only one entry over here? Forget collisions. Suppose I don't have collisions. Like, you know, you give me a phi I, and I get a unique row of that. Would I have only one pair like this? Look at this edge over here, and look at this edge over here, right? The tangent is the same. So I do have the same gradient orientation. But the radius orientation and the length of the radius might not be the same. Okay? So I will have over here another, so let's call it alpha I1, Ri1, and here, well, actually, let's call it alpha 1, R1, alpha 2, R2. And I might have several of this. Okay, these are all the points in this shape that happen to have the same tangent, okay, but they have different radius and different alphas. Okay, that's how I build my table. So edge detection, I have the orientation for every point. I take the orientation, use that as a key in my hashing function, gives me a location in this table, and I record in there the alpha I, Ri. I keep moving. I get the same orientation, so I go there and I add more things to this list. Okay? This is what I call my training stage. That's I'm learning how this shape looks like because I didn't have an equation. Okay? What happens at detection time? Now I give you this image and I ask the question, is this guy over here? How do I find it? How can I tell whether there is one, where it is? Maybe there are more than one. Maybe there are 2 or 3. So how do I know? How do I do the half transform to do that? What's the first step? Edge detection. Okay. Then I scan the image, right? And for every edge, what do I do?
Find the orientation.
I will have the orientation. Okay. So suppose I landed in this edge over here, and I know that the orientation of the gradient over here is some phi. Okay. So what do I do with that? I go with this phi to this table. Okay? That table will give me a set of pairs of alpha r's, alpha r's, alpha r's. Which one do I pick? All of them. I vote for this alpha r, this alpha r, this alpha r. Okay? What I'm going to do is not really voting for the alpha r, but I vote for what? A, B. Right? So I compute with each of these alpha r's, given where I am, right, where A and B should be, if this was the right alpha r. And where it will be if this was the right one, because I don't know which one it is, and this one. So in this case, I will have m votes, okay, for different possible centers. Okay? So for example, okay, this guy and this guy have the same orientation, so they will fall in the same row. They will have the same sets of alpha r's, right? So what will happen is that this guy will vote for this location, but it also will vote for something that it is somewhere here. Why? Because these are in this orientation Okay, this long on this angle. So I put that here. So this guy votes for this guy and this guy. When I reach here, this guy votes for what? Votes for this guy, and what else? Something that's here, like parallel to this guy. Right? So this guy votes for two things, this guy votes for two things. But guess what? They agree on this guy. So while this guy got one vote, this vote got one vote, this guy got two votes. Okay? So as I move along, what will happen is everybody will be casting many votes, but hopefully all of them can agree on this particular A and B if this was there. Okay? I think it's rather cool, actually. Sorry. All right. Now, can I extend this to, if in this shape over here, it was not the same size, but it was smaller version of it. How would modify the algorithm to detect a copy of it, but smaller or bigger?
Wouldn't it be the same because you're already going to be adjusting your radius values?
By how much?
By the difference of like whatever the scale is between them.
All right. So now I have one more parameter, which is my scaling factor. So like in the circles, I have the radius, okay? Over here, I have the scaling factor. So what it means is I have to know what scaling factor I'm expecting. Maybe expect half of the size and double of the size, okay? So now what I say is, if it was half of the size, where would be the center be? Okay, so what I need to do is reduce R by a half, divided by 2. If it was double the size, I multiply R by 2. And now I'm voting for smaller and larger. I don't know. Okay? And then when I count the votes, I will figure out whether I have something that's larger or not. Make sense? Okay. Can I change orientation? It's one more parameter, and how does the orientation affect things? It changes the orientation of alpha. So I figure out, 5 degrees, 10 degrees, and add to alpha. Okay. So it's a very powerful technique. Okay. Yes.
But you also change the phi, right?
The what?
The phi.
So the phi is the orientation of the gradient, of the tangent.
Yeah, but if you rotate the object, the phi also.
The phi will rotate. So we have to figure out, I rotate that phi by 45 degrees and go to this table over here. Okay? All right? Okay. What's next? Let's go back to lines. Okay? So say the half transform told me that these edges are likely to be on a line, right? So I counted, and I have a lot of counts, and these were the guys that voted for that being, so I think this is a line, right? So now I want to find the best line that fits this data. How do I do that? Least square error, right? So what I'm going to do is find the parameters of the line that best fit the data. And by best fitting, what I mean is that the sum of the square of the errors is as small as possible. Okay? So let's see how we do that. Not too dark. Okay. So I want to find the best line fitting those points. I said the equation, it was y equal ax plus b, where a and b are the slope and the intercept of the line, right? And so if a point satisfies the equation, that quantity inside the sum should be 0, right? Now, if the point is not on the line, well, I'm a little off, right? And I want those off things to be as small as possible. Okay, so what I want to do is to minimize the sum for all my data points. So I have n points, x1, y1, x2, y2, blah, blah, blah. Okay, and I write that equation, and I want to find the best a and b so that this is as small as possible. So what do I do? What's the tool? How do I solve this math problem? I'm sorry? Yeah, we'll get there, but before that, what do you do in calculus? What's the tool to find optimums like this? Derivatives, okay? So I take derivatives with respect to what? A and B, right? Those are the parameters. That's what I'm trying to minimize, right? So I'm going to take the derivative of that expression with respect to A, the derivative of that expression with respect to B, and set that to 0. Okay? Okay, so here's the derivative with respect to A. Okay? So I have a sum of the squares. So the 2 comes in front. A is a constant, so it comes out. And then I have sorry, A is not a constant. That's actually the variable I'm doing. The xi's are constants. Gets this term. Then I have the other term. And of course, this guy's, the b squared does not depend on A, so it doesn't appear in the derivative, right? And the y times b doesn't appear either. So I get that. I can cancel the 2's, right? So I will do that simplification. I do the same thing for the b. I get, again, this 2 times the sum of this term equal to 0. I also can cancel the 2. And now what I'm going to do is I'm going to write this prettier. Okay? And to do that, what I'm going to use is the fact that if I sum, for example, xi squared for the n samples, and I divide that quantity by n, what I have is the average or respective value of that square. Okay? And if I sum y sub I n times, and then I divide it by the number of samples, what I have is the average value of y sub I, right? And so I'm going to write that this way. So the first equation says that the average of the product of xy, right, has to be equal to the average of x squared times a plus the average of x times b. Okay? That's the first equation. Again, the 2's went away, and I divided by n, where n is the number of samples. The second equation looks something similar. I have that the average of y right, this guy, has to be equal to A times the average of X plus B. Okay? You should verify that I didn't mess up my equations. They're okay, but you should go and actually do it. Okay? Now I can put it in a matrix, right? I can write this in a matrix form, and this is how it looks like. Okay? So what it says is I have two equations of linear equations where A and B are my unknowns, and X, Y's, and the average of X, Y's, and the squares, they all came from my data, right? I took my data and averaged the X, I averaged the Y's, I averaged the products. Okay? Yes? Everybody happy? Now, we have been talking for a while about lines and equations of a line, and when I do this, you say, but Octavia, you told us that a slope-intercept equation is not the best equation to work with. Right? What happens with that equation in here? What it's doing is making the errors just on the vertical direction. It's a bias equation. Okay? It's saying that I'm off by moving the point up and down, but it's not. It has no noise in the X direction. Okay? So let's change the problem. And instead of working with this representation, let's work with this representation. Okay? So now what I'm saying is my points are off of the line, and they're off by either because they fall down or they move right or left. Okay? So I have noise both in the Y variable and the X variable. Okay? And I want to do is, over here was minimizing the sum of the squares of these lengths. What I'm going to be doing over here is I'm going to minimize the sum of the squares of these distances. Okay? How does the problem change? If you haven't seen this before, by the way, this is what's called total least squares. Okay? Because we're doing least squares not only on the Y direction, but also on the X direction. Okay? Now, how do I write the optimization cost in this case? How did I write the optimization cost over here?
Distance from the line in the Y direction.
Right. So over here was easy, right? It was the difference between the true Y and the Y I wanted. Okay. So how do I do this? What I need to do here is find the distance from a point to a line. Okay. So if I give you the equation of a line and I give you a point, how can you tell how far that point is from that line? What's the distance? How is that distance computed? So I give you this equation. Everybody agrees that's the equation of a line, right? And now I don't have the problem of slope-intercept, right? This equation can represent any line. Doesn't matter whether it's vertical, horizontal, any angle, okay? And I give you a point, P. How much is this distance, D? How do I find D? So this guy has coordinates xp, yp. How do I find that distance? Anybody remembers? No? Okay. So what I need to do is plug in this guy in that equation. And will give me something, right? If the point was on the line, how much there would be? 0. If the point is not on the line, it's related to the distance, but not quite yet. Why is that? Why cannot be just the distance? The way I wrote it. Let's say you give me, I don't know, a number f. Okay? Is this distance equal to f? What happens if I multiply this equation by k? Is the same line or not? Same line, right? So if I multiply k, f. So obviously cannot just be the distance, right? What do I need for this to be the distance? I need some way of normalizing this k. Okay? And actually geometry is such that this is the distance if, let me erase the k. If I normalize such that a squared plus b squared is equal to 1. Okay? All right? So, given a point and a line, the distance from the point to the line is found by plugging in the coordinates of the point on the equation of the line, subject to the constraint that a squared plus b squared is equal to 1. Okay? So now I can write my optimization cost. Okay? So I want to minimize the sum of these square distances, right? So I'm going to plug in my numbers x, y, for each data point into the equation line of the parameters that I don't know, a, b, and c. Those are the parameters of the line I'm trying to find, subject to the constraint that a squared plus b squared is equal to 1. Because now that equation represents the sum of the distances, of the square of the distances. Okay? So before, what I did is I took the derivative of the objective function. What do I need to do here to optimize it? How do I find the optimal A, B, and C? I also take derivatives and set them to 0. Right? How do I deal with a constraint a squared plus b squared equal to 1? Louder? Lagrangian multipliers. Okay, so what I'm going to do is I change my objective function to this, where I add the constraint, multiply by lambda, where lambda is the, the Lagrangian multiplier. Okay? And now I need to take derivatives with respect to A, B, C, and lambda. Okay? And we're going to do that, well, either on Tuesday or, I don't know, after the exam. So let's finish here. Again, if you have an objection for moving the exam from Tuesday to Friday, please send me an email tonight. Midnight is the deadline. If I don't hear from anybody, then the exam will be moved to Friday the 13th. Hope you're not superstitious. Okay? And in that case, if we move the exam, then what happens is that on Tuesday we will have the review session. Okay? If we do not move the exam, we'll be on Tuesday, and then we have a review session on Friday, this Friday. Okay? See you Friday.